All right. Welcome back, everyone, to another 1W-MINDS seminar. I'm really excited today that our speaker is Professor Joel Tropp. Joel is a Steele Family Professor of Applied and Computational Math at Caltech. He does research on a wide range of areas, from data science, applied math, numerical algorithms, and random matrix theory. Joel got his PhD degree in computational applied mathematics at UT Austin in 2004, and he joined Caltech in 2007. Joel has won multiple awards. He was recognized as a highly cited researcher in computer science every year from 2014 to 2018. He's a co-founder and section editor of the Siam Journal of Mathematics and Data Science, SIMOD, and he was a chair of the 2020 inaugural Siam Conference on the Mathematics of Data Science. Professor Tropp was also elected as a Siam Fellow in 2009 and an IEEE Fellow in 2020. As I said, I'm really excited to hear about his sketchy decisions. So thanks, Joel.
All right, thanks, Ryan, and thanks to the organizers for the invitation. It's great that we're able to join together as a community. I haven't talked to anyone for 2 years, so you can hear my voice is maybe a little bit rough, but I hope we can get through it. Okay, so I'm going to be talking about a research project that y'all may have heard bits and pieces of over the years. It took us a long time to bring all of this together because we really wanted to make sure that the algorithm that we were proposing actually works. So I'd like to highlight the contribution of Alpert Sever, who is now an assistant professor at Umeå in Sweden. He is really the engine that made all of this go. All right. So the first thing I'd like to tell you about is a motivating application of microscopy, which leads to a large-scale semi-definite program that's challenging to solve in practice. And then I'll tell you about some new ideas that we developed to actually accomplish this kind of task. So let me remind you about the fundamental challenge in the field of microscopy. You have a choice between having a wide field of view and having high resolution if you use a conventional lens, simply because of the limitations of the optics. So here is a slide of some tissue, and we have two pictures of this little square here. On the left, you can see what it looks like if you use a 20x objective. And in that case, you can get a very detailed image of what the tissue looks like here, but you can only see this tiny little square. If you use a 2x objective, you can see the entire slide, but it's all blurry like this, so you can't really appreciate the fine details or maybe perform the kind of diagnostics or pathology that you would like. So my colleague Changwei Yang invented a new kind of microscope that allows you to achieve both field of view and resolution simultaneously using computational methods. The idea behind this microscope is simple. You've got a sample like that tissue that you'd like to image, and you have an ordinary microscope, so just a lens with a light detector. Think of a digital camera. And the idea behind this microscope is that instead of collecting one image of the sample, you're going to illuminate it from different directions using an LED array. And you'll collect one image for each illumination. You'll build a stack of images, and then you'll solve an optimization problem to achieve the super resolution. So you'll be able to get a high resolution image across the entire field of view. Now, from a sort of mathematical point of view, by shifting the direction that you illuminate the sample, you're shifting the transition function around in the Fourier domain. So you can see that you're getting different information about the object. The challenge here is that effectively what's happening is the lens is computing a Fourier transform and a low pass filter, but this detector here is typically incoherent, and it can't record the phase of the light that impinges on it. And so you only get partial information about the transition function. And as a consequence, you need to solve a phase retrieval problem to be able to perform imaging in this setup. Okay, so here's a little example. Here's a slide that has a picture of some red blood cells infected with malaria parasites. If you image it with this ptychography microscope, you get, in this case, 29 illuminations, each of which is 80 by 80. And by solving this optimization problem, you can reconstruct the X gradient of the intensity and the Y gradient of the intensity by some means that I haven't shared with you yet. And this top picture is an image of what the phase looks like after it's been reconstructed. So you can see from these really terrible low quality images, we can produce high quality images using this computational procedure and this more interesting experimental setup. You can see in particular that in this blood cell and this blood cell, there are malaria parasites, those little rings, and that's something you might not be able to detect from these much lower quality images that you've extracted directly. Okay. So here's how this works from a mathematical point of view. So we model the action of this microscope as collecting a collection of measurements obtained by taking the unknown sample transmission function. You can think of this as a vector, forming inner products with some known measurement vectors, which model the action of the microscope. And then we compute the squared magnitude of that number. That's the action of the incoherent detector. And then typically we also add a little bit of noise to model the fact that these measurements are measurements. Okay, so these AI are essentially low-pass filters at different parts of the Fourier domain. And to figure out what these are, you need to calibrate the microscope. We're going to assume that those are known. Now, the goal here is to figure out what the unknown sample transmission function is given these measurements BI that we record, and with knowledge of the AI, but without knowledge of psi or xi. So we can pose this problem as an optimization problem of trying to find a guess x for the sample transmission function that yields the same phaseless intensity measurements and that minimizes the loss between those measurements and the those synthetic measurements and the actual observed data. Okay, and we'll sum this up over the entire collection of measurements. Okay. As usual, we'll assume that the loss is convex in its first coordinate, but nevertheless, this overall objective function is not convex because of the presence of the absolute square here. It's not a convex function of x, which makes this a challenging problem to solve in practice. All right, now how big is the problem? It's not that bad. For the malaria example, the dimension n of the vector, the number of pixels in the image, is about 25,000. And the number of measurements D is 185,000, 200,000. So it's a sort of small to medium optimization problem, but nevertheless, it can be pretty challenging to solve because of this non-convexity. And this is the point we'd like to address. Now, there is a convex approach to solving these problems, which is pioneered by Bernard Bodman, Pete Casazza, Edidin, and Radu Balan in their work in 2009. I don't think that they get enough credit for their contributions to this approach. So they observed that you can solve phaseless reconstruction problems by lifting. So here's how this works. We take this squared inner product, we write it out in terms of some vector transposes. So A transpose X, X transpose A. Then we notice that the matrix XX transpose here can be given a name, capital X, and that this matrix capital X is rank 1 in positive semidefinite. Now, all we've done here is change variables, and we wind up with a new optimization problem where the variable now is a matrix X instead of the vector little x, which is simply a description of the sample transmission function. So now we have the loss of this linear function of X as compared with the observed measurements BI. And we know that the matrix X has to be rank 1 and positive semidefinite because it's this outer product of a vector with itself. Now, we know what to do with this kind of problem. we follow Mariam Fazel's lead, and we drop the rank constraint and replace it with a trace constraint to obtain a convex optimization problem. So this was Mariam's thesis back in 2001. It dates back to work in the control literature. And what you would achieve by this mechanism is an optimization problem in a matrix variable with a convex objective function in the variable x, subject to a trace constraint, which is linear, and a positive semi-definite constraint on the matrix, which is a convex constraint. Now, that's great. We've converted our original non-convex problem into a nonlinear SDP, a semi-definite program. And the challenge is that we still need to estimate the sample transmission function from the solution. And so we're going to do that simply by reporting the maximum eigenvector of the solution x star to this optimization problem, which in principle we ought to be able to solve. Okay, so this is our guess for the unknown sample transmission function, which is a vector, not a matrix. Okay, so this is great. We've replaced a non-convex problem with a convex problem we can actually solve. But we've got a problem now. The matrix X doesn't have n degrees of freedom like the sample transmission function. It has n squared degrees of freedom, which in the case of the malaria example is about 655 million variables. So this is not a small problem anymore. And most off-the-shelf SDP solvers can't do a damn thing with this, in part because it's not even a standard form SDP. It's got a nonlinear objective. Okay, now you ask yourself, I know all of these fantastic non-convex algorithms, and there's so many theorems. There are ever so many theorems about these algorithms that tell me amazing things will happen. Why do I need this convex formulation, which is so hard? Well, the answer is here right before your eyes. These non-convex algorithms that have received so much attention don't work for this kind of application. These measurements are not very well conditioned that come off this microscope. If you try and use gradient descent to solve this phase retrieval problem, it gives you garbage. It's worse than the initial images that you extract. It's truly, truly appalling. So you might say, oh, but I know this other method for solving large SDPs. You know, when I just want a low rank solution, it's the Burr-Montero method. It replaces the matrix X by a factorized version, YY transpose, where Y is a tall matrix that maybe has 5 or 10 columns or something like that. Why don't I try Burr-Montero? Well, you can do that. It's sort of convex. I mean, somehow it's a bit less non-convex than the original problem. You get an image, but you can see that there's really high background variability, which again impedes the diagnostic value of this image. Are there malaria parasites here, or are these just artifacts? I mean, probably a well-trained radiologist could tell you the answer, but nevertheless, this is not a high quality image. On the right here, I have another image that has low background variability. The locations of all the cells are clear. You can see the rings from the parasites. And I assert that this is obtained by solving that convex SDP. But the question is, how are you going to achieve this, given that the SDP is 655 million variables? Okay, and so that's our goal today, is to talk about some of the ideas that go into developing a practical solver for this kind of problem. Okay, so here's some of the challenges. In data science, we often encounter large but very structured SDPs. A lot of the time, the SDPs don't have complicated problem data. So in the case of this phase retrieval problem, you just have D measurements, and the number of measurements is actually a lot smaller than the number of entries in the matrix variable. A lot of the time, the solutions to these SDP are not general matrices, but they're actually well approximated by low rank matrices. So in the case of this phase retrieval problem, you know, we asserted that we only want to produce a rank 1 solution. In fact, because of the physics of the microscope, you really want a solution that's got slightly higher rank, maybe rank 5. So this situation where the solutions to the SDPs are low rank matrices is extremely common. It comes up in rank minimization SDPs, like in Mariam's thesis. Every weakly constrained SDP is a low rank solution because of the results of Sasha Barvinik and Gabor Pataki. There are also SDPs that have low rank solutions just because of the structural properties, like the optimal power flow SDPs developed by my colleague Stephen Lowe. So what are the challenges? It turns out that computation's bad, but storage and communication are really the limiting factors. Moving around this amount of data is expensive. And one reason we really can't solve some of these big SDPs is simply because we can't write down the matrix, which is one of the things that Burr and Montero were trying to address back in 2003. And so the challenge is that we would like to design practical, correct SDP solvers, and we're going to really zoom in on the storage. We're really going to try and find a method that provably solves these SDPs but uses as little storage as possible. And in particular, we're not going to be allowed to write down any matrices that have n-squared variables in them. Okay, so this brings me to sort of a general framework, a model problem, and we're going to develop algorithms in this context. And this is a nonlinear SDP. And we're going to try and build a storage optimal approach, and we'll talk about what that might mean. Okay, so I'm going to frame a problem which you might call a convex low rank matrix optimization problem. It has the following form. It's got a matrix variable X, which is an m by n Hermitian matrix, which belongs to the set alpha times delta n. So delta n is a set of positive semi-definite matrices that have trace 1, also known as the density matrices, and alpha is a scalar. So this scales to trace up to equal alpha. Okay, so these are m by n positive semi-definite matrices with trace alpha. And among this class of matrices, which is a nice convex set, I would like to minimize an objective function f composed with some linear map that extracts vector data about X. Okay, so you should think here that A is a linear map that reports linear measurements of an m by n matrix. So in the case of this microscope system, this is the thing that reports the squared intensity of the pixels in the detector. And you should think about f as being a loss function as compared with some observed data B. But we don't need those assumptions, and carrying around B can complicate the notation. So again, A is a linear map that takes an m by n matrix and reports D linear measurements. And then we run those D measurements through a convex loss function F. It's typically the case in applications that the number of measurements D is way smaller than n squared. And furthermore, it's often the case that we anticipate that the matrices X that solve this problem are low rank or close to low rank. This is what we're going to try and get. And as I've indicated, this models the convex ptychography problem, and it models a ton of other problems in signal processing, statistics, and machine learning that have a similar form. Okay. So briefly, any questions on this problem formulation? So I see one. Yes. Felix?
Yes, there's one question in.
I see one question in the Q&A. Is the optimal X always rank 1? The answer is absolutely not. Typically, the solutions to this problem are full rank or may have moderate rank, but they're not very often going to have rank exactly 1. So,
and I was wondering, do you know any theory for the ptychography problem that convex optimization works so particularly well? Or
frankly, I'm more interested in whether it works than improving theorems about this. No, so in short, we haven't done theoretical analysis of this.
Thank you.
Yeah. Okay. Any other questions? Okay. So here's the model. This is the problem that we're going to be targeting. Later on, we'll pass back to a general linear SDP. Okay. So here's the thing. As I said, the SDP doesn't have low rank solutions in general. And in fact, it's MP hard to solve this problem if you add the side constraint that the rank of the matrix X should be smaller than some number R. That's bad news. So we're going to perform a sleight of hand. We are going to instead try and find a rank R approximation X hat to a solution X star of the SDP. Okay, so the SDP has solutions. It's an optimization problem. We're assuming that they're attained, the minima are attained. And for one of those minima, we're just going to take that matrix and try and find a low rank approximation of that matrix. Okay, that's not a problem. And formally, this means that we want X hat to be almost as close to X star as the best rank of our approximation of X star is to X star. Okay, so we want X hat to be comparable in quality to the best rank R approximation of X star. In particular, if the SDP has a low rank solution, then X hat had better equal X star, okay, because the right-hand side is 0. All right, so in the special case that the SDP really does have low rank solutions, we're going to nail them by chasing this objective. But on the other hand, we've somehow avoided the NP hardness. Okay, so this is our target, low rank approximation of a solution. And now the second question is what kind of storage bounds we can hope for. So we need to take a step back and make the problem a little more abstract to get our hands on this. So we're going to assume that we actually have access to the linear map in this problem formulation via some black box operations. So you shouldn't think about these as matrices. You should think about them as linear operators that take, or more generally, functions that take inputs and produce outputs. So the two operations we're going to be interested in are the following. We want to be able to take a vector U and report the measurements of the rank 1 matrix UU transpose. So this is a map from n vectors to r vectors, to d vectors. Okay. So in other words, given a rank 1 matrix, we can compute the measurements. All right. It's obviously very easy to do for this ptychography problem, where A just takes some squared intensities of inner products. Okay. Second, this is a little more complicated. We'd like to be able to apply the adjoint of the measurement map to a vector Z, which produces an n by n matrix. And then we'd like to multiply that n by n matrix by a vector U. So this is sort of a bilinear function again. And this takes a pair of an n vector and a d vector and reports an n vector. Why are these the operations? Well, in some sense, these are the right ones because they work. But generally speaking, you're going to need some way of getting your hands on what the matrix, what the operator A is and its adjoint are doing. And this is just the way we've chosen to quantify that. I'd like to argue that in a lot of applications, these operations are very straightforward to implement. And the key fact is that we don't need a lot of storage to write down the output of these operations. We can control what we put in, but we don't control what comes out. And as a consequence, we're going to be stuck paying n plus d storage just to write down what comes out of these black boxes. Now, the second ingredient is that we'd like to write down a rank R approximation of a solution to the SDP. And so if we write that in matrix in factorized form, like an eigenvalue decomposition, we need about Rn storage to write down that matrix. And so we're going to be paying this much storage to write down a solution to a general optimization problem. We can't avoid that either. And so we're going to say that an algorithm for this nonlinear SDP has optimal storage if its working storage cost is proportional to D plus Rn rather than the n squared cost of writing down the entire matrix variable. So we're trying to reduce the storage cost from n squared down to something that's closer to being proportional to n. All right, so that's the goal. And now I'm going to tell you about an algorithm that achieves this goal. It's called sketchy conditional gradient method, SKETCHYCGM. So here's how this works. Abstractly, we're interested in solving an optimization problem that minimizes a function g of a matrix X that has trace 1 and is positive semi-definite. So this is the abstract problem that we're going to be trying to solve. And this is a simplification of the nonlinear SDP that we talked about a minute ago. Okay, so I've drawn here the constraint set for this problem. As you know, delta n is a pentagon. And here's how this algorithm works. We'd like to take a current iterate X and improve it. That's what iterative optimization algorithms do. And gradient methods normally would take the gradient of the objective function g at the point X, and the negative gradient is the direction of steepest descent locally. Conditional gradient does something a little bit different. What it does is it takes a negative gradient and walks in that direction as far as it can in the set, keeps going until it can't go any farther in that direction. It's going to arrive at an extreme point. And given this extreme point H, what the conditional gradient method does is it averages the previous iterate X with this update direction H to obtain a new iterate X plus, which is an improvement over X. Okay. So again, H is the matrix in the constraint set Y that is most correlated with the negative gradient, and the update X plus is the average of X and the update direction. Now, the reason this is an appealing algorithm for solving these matrix optimization problems is that we know the extreme points of this set of trace 1 PSD matrices. They're rank 1 matrices. Okay. So we can always write these extreme points in the form UU transpose. And moreover, after a moment's thought, you realize that U is actually just a maximum eigenvector of this matrix, the negative gradient of G at X. Okay. So we can obtain an update direction by computing a maximum eigenvector of the negative gradient. This is a relatively cheap operation, and the updates are very simple in form. Okay, so here is code that implements what I just described to you. You start at 0, you compute minimum eigenvectors of the positive gradient, you form an update direction, you average the update direction into the previous iterate, and then you continue. Here I've used the fact that the objective function in our problem is the loss F composed of the measurement map A. And so the gradient has this sort of complicated form, and you can start to see where A and its adjoint come up. And we know that this algorithm converges at a rate of 1/t after t iterations for nice objectives F. Okay. Now, how do we get hold of these eigenvectors that we need here in this step? So Martin Yagi observed back in 2013 that you can combine the conditional gradient method with the randomized Lanczos algorithm to compute eigenvectors. I don't want to talk very much about this, but I'll just give you a few sentences. So what the Lanczos method does is to minimize the Rayleigh quotient of a matrix M over the subspace spanned by powers of M times a starting vector omega, which you should think about as random. So this algorithm only requires matrix vector products with the matrix, which are cheap. And in our context, we're going to be able to compute them with our primitives. And a remarkable observation due to Kuczynski and Wozniakowski back in 1992 is that if you draw this vector omega, the test vector at random, then you can actually approximate the minimum eigenvector of the matrix M, regardless of the spectrum of M. It doesn't have to have a spectral gap or any of the other things that the classic analysis, the power method or Lanczos method would require. And Nicolas Boumal reminded us that the randomized Lanczos method can be implemented with storage order n. And so this is a very cheap approach to getting hold of these eigenvectors. All you need to do is be able to multiply by a matrix. Okay. Now, that's sort of where things stood. People proposed to use CGM for these problems. Unfortunately, it needs thousands of iterations to converge. I mean, I really mean thousands. And what happens is that even though each iterate has only rank 1 larger than the previous iterate, nevertheless, after thousands of iterations, the rank of the iterates can get quite large. It increases without bound. And as a consequence, this algorithm requires high and unpredictable storage. You see a lot of authors in the past talking about how this is a storage efficient algorithm, but this is just not true. This algorithm is not storage efficient because the matrices that arise during this computation actually are pretty high rank. and can't be written efficiently. So we noticed an opportunity back in 2017 that you can modify the conditional gradient method so that it works with optimal storage. So how does this work? There are a few ideas. I'll show you how this pans out in the pseudocode. First of all, instead of working with the matrix variable X, we're just going to forget about the matrix variable. Instead, we're going to drive this iteration with what we call a state variable Z, which is a short vector of length D, which is the set of measurements of the matrix variable X. So instead of working with matrices when we run this algorithm, we're going to work with measurements of the matrices. Okay. Second of all, we need to know the matrix X if we want to solve the optimization problem. It's an optimization problem over matrices. So we're going to achieve this by maintaining a small randomized sketch of the primal matrix variable. Okay, so this is going to allow us to keep track of X without a lot of storage. And then after we finish solving the optimization problem, which uses D bits of storage here and Rn bits of storage here, after we solve the optimization problem, we're going to go back and look at the sketch and then reconstruct the matrix variable X by looking inside that sketch. Okay? And we're going to do that in factored form so we never have to write down a matrix of full size. Okay? That's the idea here. Okay, let's see how this pans out. So we've gone back to the conditional gradient method for the nonlinear SDP. And when you stare at this, you see right here that we've got AX sitting in the middle of the computation. And we're just going to replace that by Z, this variable obtained by taking measurements of X. Now, the problem is that we've also got an update rule here for X, and we actually need to update Z rather than X. But this is easy. This is a linear update. So we can just apply the matrix A to this update to get a linear relation for the state variable Z. So we get an update rule for the state variable Z by applying the measurement map to this update. And here's what we obtain. Okay. So now we have an algorithm called state conditional gradient, which produces measurements of a solution to this nonlinear SDP. And it does so by iterating on the state variable. And here you can see A star times a vector. And we're using this inside randomized Lanczos, which takes matrix vector products. So here we've got the A star primitive. Apply the adjoint to a vector and multiply it by another vector. So we can implement randomized Lanczos if we have this primitive here for A star. Here you see that we're applying the measurement map A to a rank 1 matrix. Oh, but that's the other primitive that we required to allow us to access A. All right. And here we've just got this simple linear update rule for the state variable. So this is great. We've reduced the storage of the algorithm from n squared all the way down to n plus d because the only variables here are vectors of length d and vectors of length n. But there's a problem now. We've totally forgotten what the matrix is. And that's what we want. We want the matrix because the matrix is the thing that solves the problem. I mean, no one cares about the state variable. I mean, we already know the measurements because that's what we started with. So what are we going to do? We need to remember the matrix. So the way that we're going to approach this problem is using sketching. So a technique from randomized linear algebra. So here's what we're going to do. Instead of keeping track of X, we'll keep track of a sketch. So we're going to draw a Gaussian matrix that has not too many columns. So say twice the rank of the solution that we're after. This is a parameter that we specify in advance. So we draw and fix this Gaussian matrix. And the sketch of a matrix X is simply multiplying X on the right by the Gaussian matrix to obtain a tall matrix Y. So instead of watching the matrix X, the m by n matrix during the algorithm, we're going to watch the tall matrix Y. And at any given time, if X is the iterate of the original CGM algorithm, Y is going to be the sketch of that iterate. And this is what we're going to update during the algorithm. Now, once again, we remember that the update rule for X is linear. And so we can obtain update rules for y just by multiplying this on the right by omega, the random test matrix, the dimension reduction map. And so y is updated linearly using this relation. And since the updates are really just these rank 1 matrices, this is very cheap to implement. So we can update the sketch at each iteration very, very efficiently. And instead of storing this m by n matrix, we only need to store a tall matrix y. All right. Now, the remarkable thing is that given knowledge of the test matrix omega and given knowledge of the sketch of x, using this maybe not so obvious formula here, we can compute a matrix x hat, which is a rank R approximation of the matrix X sitting inside the sketch, and which has a guarantee on its quality. It's almost as good a rank R approximation of X as the best rank R approximation. Okay, and so this is what's going to allow us to unpack a solution to the problem after we've run through the optimization. And the great thing is that this whole sketching process only uses order Rn storage. So we're on track to building a storage optimal algorithm. Okay. So here's how this works. I've just added in the sketching method to keep track of the matrix X. I'm not going to talk very much about this. I just want to point out that adding the sketch only adds, 11 lines of pseudocode. This is the entire algorithm for the SKETCHYCGM method. It takes a little bit more care to implement in a numerically stable fashion, but at the bottom of it, this is enough to solve this optimization problem reliably. Okay, now we have a theorem, since Felix likes theorems. Here's what the theorem says. This algorithm I just described to you has the following properties with high probability. At each iteration, SKETCHYCGM implicitly computes a matrix xt, and these matrices xt converge to the solution set of the nonlinear SDP. But the thing is that we don't actually have hold of these xt. These are the iterates that conditional gradient would generate that somehow are hiding in the background. What SKETCHYCGM actually produces is a rank R approximation x hat t of these implicit iterates that are hiding in the background. So at each iteration, SKETCHYCGM spits out a rank R matrix that approximates the true iterate. Okay. And it accomplishes this task using the optimal storage cost d plus Rn, which is argued is really the best you can hope for. Okay, now, what does this have to do with solving the problem? So making some sort of modest assumptions on the SDP that allow me to write down something simple for discussion here in a talk. If the solution is stable, and say if the solution has a low rank, then the iterates produced by this algorithm are nearly as close to X star as the optimal rank R approximation. The objective function converges to the optimal value, and it does so at a rate of 1/t. So in short, if this problem actually had a low rank solution, SKETCHYCGM would find that low rank solution and it would converge at a rate of 1/t. If the problem does not have a low rank solution, this algorithm instead produces a sequence of rank R matrices that are almost as good as the best rank R approximation of the solution. Okay, so it achieves what we set out. And you can write down the resource costs, but these are messy, and so I want to leave this aside. Okay, let me pause and ask if there are questions about this algorithm. If you have sort of more general philosophical things, I'd like to save those for the end. But if there are anything about the mechanics of this algorithm that might not have been clear, let's try and clarify that now. Okay.
Yeah, there are a couple questions in the Q&A.
Yeah, so let me answer the question that Kyle asked. So where in the algorithm are the constraints enforced? That's a great question. They're enforced automatically because the constraint set is convex. And if the iterate X is in the constraint set, and we average it with another point in the constraint set, the update direction, which by construction is in the constraint set. By convexity, the iterates remain in the constraint set. So we actually don't have to do anything to make sure that the iterates remain feasible. Okay. So it's a remarkable feature of this algorithm. We don't have to worry about the constraints. I'm not sure I understand this question about a minimax framework. You can certainly, I mean, this is a convex optimization problem, so it's natural to minimize it. We'll talk in a minute briefly about saddle point formulations, but I'm not sure that's going to address the concern either. Are there other questions?
One more, Joel, just popped up in the Q&A.
Yeah, so the learning rates or the step size here in conditional gradient are the standard choices. It does lead to optimal convergence. Anything else? Okay, good. So look, I realize this is a bit of a, let's talk about Kyle's next question about other constraints in a minute. And after the state variable is constructed, how does the objective function change? I'm not sure I understand this question either. So I'm gonna just leave that aside. We can maybe come back to this later. Okay, so in short, we have an algorithm for solving this nonlinear SDP that has optimal storage and that converges at this 1/t rate. So this nice feature. But a more interesting challenge perhaps is to solve standard form SDPs with optimal storage. I'm not going to talk a lot about this because most of the ideas are similar to the problem I just showed you. But we'd really get into the weeds if we wanted to talk about the details. So we're going to consider a more general class, or maybe not more general, we're going to consider a different model problem for the next couple slides and for the experiments, which is a trace-constrained SDP. So the idea here is that subject to some linear constraints on the matrix X, which is positive semi-definite and has trace alpha. So among matrices with trace alpha that are positive semi-definite, we're going to enforce some linear constraints given by a measurement map A. So they're D constraints, equality constraints. And over that constraint set, we're going to minimize a linear function of X. Okay. So this is a standard form SDP with an extra trace constraint. So in a lot of applications, the number of linear equalities, D, is a lot smaller than the dimension n squared of the matrix. And all of the solutions have low rank or very close to having low rank. Okay. And so our goal here is similar to before. We'd like to produce a rank R approximation to a solution of the SDP. So again, this is different from finding a low rank solution or finding the best low rank matrix that somehow approximately solves this. What we are doing is we are finding a solution and then producing a low rank approximation of that without ever using the storage needed to instantiate the matrix X. Okay, got that? So standard form SDP, not too many constraints. We want a low rank approximation to a solution. So here's how we might approach this problem. So we're going to use another algorithm called SKETCHYCGAL. And this approach essentially applies the SKETCHYCGM algorithm to the augmented Lagrangian. So here's how this works briefly. This function here is the augmented Lagrangian of that SDP. So we've generated a dual variable y for the equality constraints, and then we've put in a quadratic penalty for the equality constraints with a parameter beta. Okay, so this is a nice convex function, maybe even strongly convex in some parts of the domain. And what the CGAL algorithm does is it solves this primal problem using CGM. So it takes a primal step using the conditional gradient method to update the matrix X. To update the dual variable, it takes a gradient ascent step with respect to the derivative with respect to y. And then at each step, it performs homotopy on the parameter beta. Okay, so the parameter beta goes off to infinity, I think. I can never remember, which forces this constraint to get stronger and stronger. Okay, so that's an algorithm for solving this augmented Lagrangian form of the problem. It works pretty well, but it doesn't have any storage guarantees. And so what we've done is we've taken this algorithm that Alp designed, and we've added a state variable, so we don't have to track the matrix X, and we've used sketching to watch the matrix X instead. And if you take these innovations from SKETCHYCGM and plug them into CGAL, you get an algorithm called SKETCHYCGAL, which solves this problem formulation and converges like 1/√t, which is probably optimal for this formulation. Empirically, the convergence is really 1/t. Okay, so this is a very powerful general approach. The details of this are all in the paper, Scalable Semi-Definite Programming. It's a little bit complicated, so I just want to give you a flavor of the idea. Now, one of the questions asked about extensions. So you can extend this algorithm to all sorts of problems. It works if there's no trace constraint. It works if you have additional affine cone constraints. It works for other kinds of matrix sets like rectangular matrices with bounded spectral norm, things like that. And these are all relatively straightforward extensions of this algorithm. Okay, so we discussed that in the 60-page supplement to the paper. All right, good. Now the real question is, does this work? So these are some SKETCHYCGALs. And I'd like to show you a little bit of numerical evidence that these ideas that I was sharing with you are actually allow us to build methods for solving large-scale SDPs. So here's a sort of trial case. So you all know the MaxCut SDP, which is an SDP relaxation of the combinatorial problem of finding the largest cut in a combinatorial graph. So we applied this problem to a 10,000, we considered a graph with 10,000 vertices, which leads to a matrix variable that is 10,000 by 10,000. It's a pretty sparse matrix. And what I've shown you here is the performance of the SKETCHYCGAL algorithm for solving this instance of MaxCut. So the left panel here is the objective residual. So if you actually solve the SDP using CGAL, the black line is the objective residual as a function of the number of iterations. And these curves here show you what happens if you make low rank approximations. So a rank 100 approximation is good enough to track the residual. Rank 25 and rank 10 approximations, you start losing a bit on the objective residual. This panel is the infeasibility of the iterates. So how well do they approximate the equality constraints in the MaxCut problem? If you just run CGAL, the infeasibility goes down linearly. If you make low rank approximations, you lose a bit in terms of the infeasibility, but it's still declining. And the third panel shows you the weights of the cuts that you obtain from the iterates of the SKETCHYCGAL algorithm. And you can see that the low rank approximations don't actually affect the quality of the cuts. So as you run this algorithm for a few hundred iterations, you can see that the cut values increase and then sort of saturate at this level. This black line here is the cut you would get by solving the SDP exactly with SDP T3 to 10 digits of accuracy, and then taking the maximum eigenvectors. You can see that we're actually even getting better cuts than you would by solving the SDP to high precision. The bottom panels are the timings, which aren't that interesting, but the main thing I'd like to point out is that in 10 seconds, we can produce a cut of this graph on 10,000 vertices that is essentially optimal. It is pretty fast. Okay. Any questions on this new experiment? So this just shows the SKETCHYCGAL algorithm converges. It converges at a particular rate, and that by using low rank approximations, you're not necessarily leaving that much on the table in terms of the residual, the infeasibility, or the cut values. Yeah, so that. Do you have a question?
What is the peak that you have in the first plot?
Here?
Yeah.
Oh, you know, what can happen is that that the matrix can what can happen is that the variable can be really infeasible, and so it can make the objective residual really great, but then you have to repair the infeasibility, and so the residual goes back up.
I see.
Yeah. More questions? Okay. So the number of vertices is the number of dimensions. So this graph is 10,000 vertices, so it's a 10,000 by 10,000 matrix. The number of edges in the graph is the number of, roughly the number of non-zero entries in the matrix, C in the linear SDP formulation. Okay. But it doesn't have anything to do with the matrix X as such. Okay, good. Now, this is a full suite of experiments for MaxCut problems. We took all of the graphs in the GSET collection and all of the graphs in the Dymax 10 collection. These are all sparse MaxCut problems, and we tried to solve them using the SKETCHYCGAL algorithm. Okay, so these problems range in size from graphs on about 1,000 vertices to graphs with about 50 million vertices. And this experiment I'd like to emphasize is performed on a laptop equivalent. So 16 gigabytes of memory, one processor. Okay, so if you use classic algorithms for solving the MaxCut problem, Sadumi SDP-3, Mosaic SDP-NAL+, the storage costs just skyrocket. And the reason is because they're storing m by n matrices. And as a consequence, these algorithms fail when the number of vertices in the graph gets to be about 10,000. In contrast, SKETCHYCGAL uses a very modest amount of storage. It's enough storage to solve the MaxCut problem, essentially optimally. But as a consequence, the storage costs grow much more modestly, and we can handle graphs on 23 million vertices, again, on a laptop. Here are the timings. Once again, these fancy algorithms are slow. Their costs grow quadratically, and they die after you get to about 10,000 vertices. In contrast, if you use SKETCHYCGAL, it can solve problems, MaxCut problems on graphs with up to 23 million vertices reliably. Now, that being said, these are not exactly champion run times. I mean, these examples took a couple days. But nevertheless, these are problems that you couldn't solve before using existing techniques. So the scalability really is an enabling technology that allows you to solve these problems. I guess I should say that you could solve these problems using Burr-Montero, and its performance is actually somewhat comparable with this. But Burr-Montero actually has some failure modes. There's some problems that it can't solve. Okay, any questions on this experiment? All right, great. So we can solve huge MaxCut problems. I mean, all right, that's interesting. It demonstrates that the algorithm really is scalable, but maybe who cares? So I'd like to close with an experiment that's maybe a little bit closer to a realistic application. So let's come back to this Fourier Ptychography problem that we started out with. So here I've got a slide, 320 by 320 pixels. This is all digital, by the way. This is not actually taken off a microscope, it's synthetic. So a slide with 320 by 320 pixels of some tissue that's, I guess, infected with the Marburg virus. So something truly scary. So we took 225 illuminations, each of which had 64 squared pixels. So these are low resolution illuminations that we'd like to use to reconstruct this this image to full resolution across this wider field of view. Now, this leads to an SDP where the matrix variable has about 10 billion entries. okay? So keep in mind that a matrix with 10 billion entries requires 40 to 80 gigabytes of storage, okay? So this is not something you're going to do on your laptop easily if you need to carry that matrix around. The number of equations you obtain from these illuminations is about 1 million, okay? So that's a much smaller number. So if you start running SKETCHYCGAL on the linear SDP formulation of the Ptychography problem, nothing happens at first. After 10 iterations, you see nothing. After 100 iterations, you see nothing. But after 1,000 iterations, which takes about 5 hours, you've already got a reasonable reconstruction of the image. And by 10,000 iterations, you've actually got a pretty sharp reconstruction. Okay. So, I mean, as you can see, this was 4 or 5 days of work or something like this. So, no, actually about 2 days of work, so it's about 50 hours. So this is, again, not exactly a champion runtime. But again, this experiment was performed on a single laptop, and it demonstrates that we can solve an SDP of interest in imaging that has 10 billion variables. And so I'd like to leave you with the observation that by using new ideas that have come out of randomized linear algebra, new optimization techniques, and by really attending to the resource costs that are most serious, we're able to solve a class optimization problems that are, of wide interest, but, maybe previously were not accessible. You can't solve this problem using Burr-Montero. It's just not even applicable. And if you're interested in learning more, the paper on this project appeared in SciMods the beginning of this year. And there are a whole bunch of supporting papers on randomized linear algebra, and there's some work down here on microscopy. If you'd like to read a bit more about randomized linear algebra foundations, Gunnar Martins and I recently wrote a survey on this that appeared in Actin Numerica, and it'll give you at least some idea about what people are thinking about these days. All right, thank you so much for your attention, and I can hang around if there are more questions.